Hey friends, my name is Z and you're watching here MakesItEasy, and welcome back to a new video for A-Level for the Medicine today. We have a new chapter for CP1 for chapter 5 of Volumes of Revolution. And we'll start with 5.1 for the volumes of revolution around the x-axis for the rules and examples video. And we'll get right into some integration, but before we get into it, don't forget to leave a like, subscribe, and ring the notification button so on any future videos. And we'll get right into some integration to find areas. So in GCSE or A-Level Math, we have used integration to find the areas of a region R bounded by a curve, the x-axis, and two vertical lines. Like we have this diagram over here. The area is given by the integral of y from x equals a to x equals b dx, where y equals f of x is the equation of the curve. And integration actually works by splitting the area into infinite number of small strips with width of delta x, which is the difference in x. And each of these strips have a height of approximately y, or like y. So the area of each strip is delta a, the change in area, is equal to y times delta x. And the total area is approximately the sum of these strips, or the sum of a is equal to the sum of y times delta x. And the exact area is the limit of this sum as delta x tends to 0. So what it means is that we have this graph over here. Let's say we have this curve, this line, this curve. So basically, let's say we want to find the area between here, between this line here and this line here, right? What we would do is that we would split into infinitely small, or like infinite small rectangular strips or trapezium strips. So let's say we split into these kind of strips, right? So strips, and all of them have width delta x between each strip. So the exact area of the area between under the curve is when delta x tends to 0, which means that the strip gets so small that it's basically becoming an area, which is written as the integral of y. And you can notice how the integral symbol looks like an elongated s, because this integration sign basically means infinite sum of infinite small values. So the integral is mostly similar to like s, right? It's like an elongated s for that, which stands for sum, because it's basically the infinite sum of all the small strips within that area, or like within the area that you want to find under the curve. And here we have some introduction to volumes of revolution, which is what we're looking at for CP1. So we can therefore use a similar technique to find the volume of an object creating by rotating a curve around a coordinate axis. So we'll start with the x-axis first. And if each of these strips is rotated around 2 pi radians or 360 degrees around the x-axis, it will form a shape that is approximately cylindrical, right? Let's say we have this one right here. We rotate it 360 degrees to form like a roughly cylindrical shape. And the volume of each cylinder will be pi times y squared times delta x, as it has radius y, so the radius y, and height of delta x, which is this one right here. So the volume of the solid will be approximately equal to the sum of the volumes of each cylinder, or the sum of V, the volume, equals the sum of pi times y squared times delta x. So therefore, in short, taking everything into account and simplifying everything, the volume of revolution formed when y equals f of x is rotated through 2 pi radians around the x-axis between x equals a and x equals b is given by the volume when the volume equals pi times the integral of y squared from x equals a to x equals b, and integrated with respect to x, like so. So it's quite important, a few things here. Remember that there's a pi in front, and remember that you have to square the function, and that's very important. And we'll now look at an example for the volumes of revolution. So the diagram shows the region R, this diagram over here, which is bounded by the x-axis, the y-axis, and the curve with the equation y equals 9 minus x squared. The region is rotated through 2 pi radians around the x-axis. Find the exact volume of the solid generated. So we know that we have to find this point right here in order to find the area under the curve. So in order to do that, we will just set y equals 0, because in this case, y equals 0. We need to find the x value. So it'll be 0 equals 9 minus x squared, right? Because that's the original equation, like so. So therefore it'll be x squared equals 9 and x equals plus minus 3. But in this case, we're not looking into the -3 region, where there's a -3 here. We're not looking into that. So we're only looking at the +3. So x equals +3. So therefore, we can now find the volume. So the volume equals pi times the integral of y squared, so which is 9 minus x squared dx from x equals 0, because there's the lower bound right here, to the upper bound, which is 3, so 3. So we can now basically just simplify it to get from 0 to 3, like so. Oops, it's a bit of a weird symbol. Now we have to expand the bracket, which is equal to 81 minus 18x squared plus x to the power 4 dx. Simplifying everything, you get pi times the 81x minus 6x cubed 6x cubed plus 1 over 5 x to the power 5, and write the bounds from 0 to 3. So we can now basically just simplify the whole thing, which I'll type into my calculator. So by substituting the upper bound first, you know it's 81 times 3 minus 6 times 3 cubed plus 1 over 5 times 3 to the power 5, and that gets us 648 over 5. And the lower bound is just 0, because you know that all terms have an x, and 0 times any number is 0, and it will be 0. So therefore the whole volume will just be 648 over, let me just write it bigger. So it will be 648 over 5 pi, and the unit, there's no unit given, so it will just be unit cube, like so. And the last example, the finite region R which is bounded by the curve C, the x-axis and the line x equals 125 is shown in the figure down below. The region is rotated 360 degrees about the x-axis to form a solid of revolution. Given the curve has an equation y equals this one right here, use calculus to find the exact volume of the solid of revolution. So we define the lower bound right here. So basically just set y equals 0, so it'll be 0 equals x to the power 2 over 3 minus 9 and a half to the power of a half. So just basically rearranging to get x to the power 2 over 3 equals 9. So x equals 9 times 9 over to the power 3 over 2. So this gets us, let me just put into my calculator. So 9 to the power 3 over 2, and that gets us 27, like so. So we know that this point right here is 27. So we can now basically just find the area, the volume. So volume equals pi times the integral of y squared, which is x to the power of 2 over 3 minus 9 to a half, everything to squared dx from x equals 27, which we found just now, to 125, right? So we know that this cancels out because a power of a half times a power squared cancels out. So it just be pi times the integral of x to the power of 2 over 3 minus 9 from x equals 27 to 125 dx. So therefore this simplifies to, let me just write down here, pi times 2 over 3 plus 1 is equal to 5 over 3, and integrate that, so it will be 3 over 5 x to the power of 5 over 3 minus 9x, and the bounds are 27, or the limits are 27 and 1 to 5. So it will be pi times, let me just substitute 1 to 5 into it. So the upper bound will be 3 over 5 times 125 to the power of 5 over 3 minus 9 times 125, and that gets us 750, minus the lower bound, which is 3 over 5 times 27 to the power of 5 over 3 minus 9 times 27, which is minus 486 over 5. And simplifying that will get us 750 plus 486 over 5 times by pi, and that gets us 4236 over 5 times pi and unit cube, and that's the final answer. And this is for this short video for 5.1 for the volumes of revolution around the x-axis. And I hope you will find it useful and helpful, and if you did, please leave a like and subscribe and ring the notification button to know any future videos. And if you have any questions or any comments regarding my channel or my YouTube or my Instagram, you can leave them down below and I'll reply to them. And check out my social media in the description, for example YouTube or LinkedIn or Instagram. And if you need any learning resources or any teaching resources, you can check out my website in the description, or you can type it out in your browser www.MakesItEasy.com. And hope you enjoyed this short video on the volumes of revolution around x-axis, and I'll see you all in the next video, which will be questions for the volumes of revolution around x-axis, which will be fun and interesting because calculus is fun. But anyways, I hope you will find it useful and helpful, and I'll see you all in the next video. Until then, stay safe and happy learning.